Alright, let's talk about what are called pH curves. This is what you're going to be doing in Monday's lab. You're going to be making a graph with a pH curve. And this is the first time we've done a lab where we've had data collected where I'm not going to ask you to give me a table. I only need the graph. That's because the table is going to be so huge, so much data that it's not really worth putting down. But you're going to have a graph. On the Veneer Logger Pro, you're going to produce a graph. And what's going to be down here on the bottom will be the volume of the base solution. Okay, now you'll have to put in the units of measurement and so forth down here and the species of that base. But right now we're talking about a more general sort of idea, okay? And what's on this graph over here is the pH. Well, that side of the graph is the pH. You'll have to figure out a title. You have to have a figure label before you turn it in. But you guys know all that, right? Alright, so we're going to start. I'm going to show you some typical graphs that will be produced from this process. Now, when I say typical, we need to be very careful about that because this is a general idea of what's going to happen. It won't be exactly what you're going to see. Every lab group will have a different acid. You won't know what that acid is. But there are some things you're going to be able to tell me from this graph about that acid in terms of helping figure out what kind of acid it is. One of the first things you'll be able to tell from this graph is whether or not it's a strong or weak acid. You can tell that even though you don't know what the acid is from the shape of the graph. Or from, I guess we could say the shape. And then you can also tell me from the shape of the graph whether the acid is monoprotic, diprotic, or triprotic. From the graph, you'll be able to tell me the what's called the equivalence point, and that comes in pH units. By the way, there actually is no unit of measurement for pH. It's just a number. First time this semester we've had just a number. Okay? And you'll be able to tell me the equivalence point and the volume of base solution used to reach that point. With this information, you'll be able to calculate the concentration of the acid. Alright? So you're going to be able to tell me an awful lot about the acid, the unknown acid that you're working with from this graph you're producing. Now, these graphs will all look different, but we can say some things about acid or pH graphs, pH curves generally. And then the rest of it you just have to kind of evaluate as you go along. Alright, so if I have a graph that kind of starts out like this and does this thing right here and does that right there, I can tell a lot about that acid just from that shape. Okay? I can tell a lot about that acid just from that shape. I can tell because the curve started at or below 0, or if it appeared that it might have started at or below 0, but it had been diluted, so it started somewhere up here instead. Okay, so it's either it might start at 0, might start below 0, or what we can determine from the graph is that, oh, it looked like it might have started down there if we just started soon enough with a strong enough concentration. That tells me that it's a strong acid. Okay. Now, if we had done this pH curve with the hydrochloric acid that we were using in Monday's lab, last Monday's lab, hydrochloric acid is a strong acid, but our pH curve would have started up here somewhere. It wouldn't have looked like this. So we have to use some kind of, judgments here about whether it might have started down here if we had started with a stronger version of that acid. Okay? That's a little bit hard when you're starting at about 2.5. That's a little hard to tell, but we could have, if we had a stronger acid, it would have started down here somewhere. All right? So you can't make it say more than it can say. All right? You got to work with what you got. Okay? And you reach reasonable conclusions based on the evidence you have. All right. The equivalence point of this acid is right here. And what happens at the equivalence point it's where the number of acidic protons, that is to say the protons that come off of an acid, are equal to the number of hydroxide ions. Okay? And that's for this kind of titration that we're doing. There's lots of different kinds of titrations, but we're just working with an acid-based titration, typically of the type where you try to figure out something about the acid. Okay? You always use a strong base, and so you know something about the concentration of hydroxides before you start. But whenever you have the number of hydrogen ions from the acid equaling the number of hydroxide ions, you're going to have the equivalence point. And that's always the steepest point on the cliff face. The equivalence point is always the steepest point on the cliff face. Anybody here taking calculus right now? You are? Okay. Well, we're going to be using first derivatives to help us figure out that point. Have you done derivatives already? Good. I'm sure you have. You're taking calculus at this point in the semester. Right. So you can help everybody understand what a derivative is. No, not now. On Monday. Okay? All right. So derivatives, if you haven't taken calculus yet, you will learn about derivatives. That's basically what you start out learning about after you've learned some basics about notation and stuff, I think. That's what you learn about in calculus, about the first thing, isn't it? Yeah. Okay. So we'll use a derivative, and hopefully I'll have time in this class period to show you what it looks like on a graph and why it helps you figure out what that equivalence point is. Okay? All right, so let's see. We know it's a strong acid because it starts down here near 0, or looks like it might have started at 0. We know it's a strong acid. The shape of this graph also tells me it's monoprotic because there is only one cliff face. Only one cliff face, monoprotic. Now, the equivalence point typically is indicated by the pH. In other words, you say, you go over here and figure out what point on the vertical axis matches up to that equivalence point, and you say, my equivalence point occurred at pH so-and-so. Does that make sense? That's how you state what the equivalence point is. Equivalence point occurred at pH so-and-so. Make sense? Okay. The concentration of base solution is found by tracing vertically down to that line right here. So this is where you're going to get the concentration of base solution used. This concentration is very important. Sorry, it's not the concentration. This is the volume of base solution used. Sorry about that. But it's the volume and the concentration together. You know the concentration, and the volume and concentration together is going to be how you figure out the original concentration of the acid for which you didn't know. Okay? Got that? Well, we'll talk about the stoichiometry later. So once we know the volume used, then we will already know the concentration. We can calculate the concentration of the acid using stoichiometry. All right, you got that? Strong acid, monoprotic, know the volume of the base solution used. Those are the key things you get from this graph. Any questions? Yes?
So if it was like diprotic, it would have more than...
I am so glad you asked that question, and you are thinking ahead. You're right on the money. I'm so proud of you. Wow. I'm not just joking around. I really am. Okay, so let's look at that. Diprotic. Let's start with a strong acid again. We're going to start down here, and so diprotic is going to look like this. Is that what you're asking?
Yes.
You got it. So diprotic has two equivalence points. Okay, so we're going to explain what the equivalence point is by the pH registered here. Okay, then we're going to know the concentration of, the volume, I keep saying concentration, the volume of the base solution used down here. You got it. Actually, it's the volume of the base solution used to reach equivalence, and that's what's key. It's not just the total amount of base solution used, but the amount used to reach that equivalence point. Okay? Now, in our lab we did last Monday, both the acids we were working with were monoprotic. Now, what does that mean? Here's our acid, our strong acid we used on Monday. It's monoprotic because it only has one hydrogen ion that it can give away. Okay? Monoprotic means it only has one hydrogen ion to give away in solution. Now, there are types of acids that have more than one hydrogen, but some of those hydrogens might not be available to give away as an acid. The other acid we used was acetic acid, and these three hydrogens I have in the formula here after the C, those three hydrogens are actually bonded to that carbon. When you bond a hydrogen to a non-metal, that's not acidic generally. Okay, so if it's bonded to nitrogen or carbon, back that up. If it's bonded to nitrogen or carbon or sulfur. Wait a minute, that's not true either. If it's bonded to nitrogen or carbon, it's not acidic. Okay, there's not enough difference in electronegativity for acidity to occur. Okay, but if it's bonded to an oxygen in this structure, so remember we had when we did the structure of acetic acid, we said acetic acid actually had this structure if we were using Lewis formulas. Well, this hydrogen right here is the one that's acidic. This is the one that can leave and make an acid hydrogen. Normally, if it was just an OH group on a carbon, that hydrogen doesn't usually leave. You can make it leave if you have the right conditions. The difference is it's right next door to this carbonyl. So the carbonyls are kind of sucking in the hydrogens, making this really a huge electronegativity difference that otherwise wouldn't exist. That's kind of beyond the scope of the class, but I'm just trying to give you an idea of why this is an acidic hydrogen. Okay? So most hydrogens on an OH group that's on some carbon chain wouldn't be acidic. This one's acidic because it's right next door to the carbonyl. Okay? So if we were writing this out in an Arrhenius acid form, we just pull off this hydrogen here, and we'd have the acetate ion left behind. Okay? So those are our acidic hydrogens. Now, for a diprotic acid, we have to have two hydrogens that are available to pull off. Okay? So there's really only one strong diprotic acid that we're going to have any experience with in here, and that's sulfuric acid. Right? There's two hydrogens that can be pulled off. So I'm going to switch gears. I was using Arrhenius up here. I want to go to the Bronsted-Lowry theory of notation, okay? Everybody okay with that? Anybody? No objections? Okay, good. Don't hear any. All right, so with Bronsted-Lowry, we're still going to pull a hydrogen off, a hydrogen ion or a proton off. But this time, instead of just floating around willy-nilly in the water like this, it's actually joining up with an oxygen, the oxygen part of water. And so now we get H3O from that, and we have HSO4 left over. Okay? So this is the first dissociation. When I put enough base in the water to make this happen, we reach the equivalence point, this first equivalence point. Okay? And what's maybe a little bit tricky about this is we've talked about putting base solution in the water, and so the base we would expect is reacting with the acid, but we haven't shown that. So let me show you what that looks like. This is a slightly different looking equation. So let's put our H2SO4 down here again. And instead of just having it react with water, we're going to have it, we're going to show it as if it's reacting with the base part of our base. Okay? What does the base part of a strong base look like? What's that part of the formula look like? Huh? Can't hear you. OH. Okay? All the strong bases have an OH group on there. All of them we've used so far have an OH on there. Okay? So this is the base part. This is what does the work of the base. Okay? The hydroxide ion. Alright? So when we put let's say in Monday's lab we had KOH. We put that in water and we got the potassium ion. We had the OH, the hydroxide ion, and this is what's doing the work of a base. Okay? So we're putting this acid in the solution. Well, I'll tell you what. In fact, instead of doing this, let's do it this way. Let's say H3O. Okay, because that's the acid part of what's doing the work here. And we're putting in the water with the OH. And we're getting two waters. Okay? When I have the number of hydronium ions equaling the number of hydroxide ions, I've reached the equivalence point for that first hydrogen I pull off of the acid. That's just the first one. That's where we get this point in the graph right here. Yep, because we're adding base solution to it. The base is actually soaking up those hydrogen ions and neutralizing them. And when we get an equal number of hydrogen, or in this case, hydronium ions and hydroxide ions forming water, we reach that equivalence point. But that's only for the first hydrogen you can pull off. Okay? All right, now, there's a second hydrogen on this thing right here. This is called bisulfate, just in case you want to know. So if we take this bisulfate ion, I'm sorry, that's the negative, and we put that in solution with this KOH, which will give us the OH ion. Okay? Then the hydrogen is going to come off of this and join up with the OH. Well, this is what it actually does in water to make a low pH. Then once it's in water, this is actually reacting with that. So we got some crossover in our understanding of how these different equations work. Depends on what you're trying to say. Okay? I'll go back and redo these so we get at least one common way of doing it. Okay? But this hydrogen joins with this. We get some water then, and we have this sulfate ion left over. Okay? There's kind of a lot going on, and we kind of trim them down by sticking with just the stuff we want to talk about. And this is the second dissociation here. You got all that? I'm going to go back and redo first and second dissociation in a common form. Give you a common way of writing equations to show that. Alright, so our first dissociation, I'm going to write it as having the acid here, and I'm just going to put the hydroxide part of things. Or I could put the whole formula in there. Let's do that. Let's go with let's say we're going to use the same base we used on last Monday. Okay, potassium hydroxide. Can't promise it's going to be the same acid we're going to use on Monday, this coming Monday, but this is the one we used. All right. So the hydrogen ion is actually coming off of this thing. The hydroxide coming off of this thing, and they're joining together. Does that make sense? Why? Because they are really strongly attracted. Okay? I don't know. Do you have a boyfriend?
No.
Oh. Well, it doesn't help very much then. If you had a boyfriend, you'd assume you'd be really strongly attracted to that more than these other things up here. The other guys and the other girls around. Right? Okay? Kind of the same thing. Sort of. Well, hydrogen ions and hydroxide ions are really strongly attracted to each other. So they're going to... Huh? You could say that. You could call them boyfriends and girlfriends. Sure. Okay? All right. Well, if that happens then, over here on the other side, the hydrogen was pulled off of this. What's left then is HSO4 with a 1 negative charge. If I pull a hydrogen off, which is positive, we call it a proton 2. Okay? If we pull this proton off, then we have to keep everything else in the formula except that first proton. Okay? And then we also have the potassium left over, and we made a water too, H2O. So we've liberated some potassium. We freed the potassiums. Well, that's our first association. That's another way of thinking about the first association.
It doesn't always have to be with water?
When I put the acid in water, this is what it does automatically. Okay? But then after we put the base in, this other thing is happening here. So we could really make this complex with a whole bunch of different ions and things. But what's happening is we're really forming the hydronium. The hydronium then is reacting with the hydroxide, and we're forming 2 waters. I mean, we can go that way too. What you want to do is illustrate what's happening in the most practical way. Okay? But what we're doing here, since we're neutralizing an acid with a base, we're pulling a hydrogen off and joining up with a base. When the number of hydrogens and hydroxides are equal,
Would you get the same thing if you added the water and then took the results of that and then did it with the base? Like if you added H2SO4 and then added the KLH2, would you get the same thing?
the equation is going to come out to be the same, roughly. Okay? Depends on what you're trying to illustrate. Okay? When the number of hydrogen ions or protons is equal to the number of hydroxide ions, then you have reached the equivalence point. Okay? But this is just for that first hydrogen coming off. That's the first equivalence point. Since it's a diprotic acid, we got a second equivalence point. The second equivalence point occurs when we keep putting base in the solution, putting more hydroxide stuff in there, and what we have then is when we put enough in there, we can pull off this second hydrogen. So the hydrogen's coming off of this now. This second hydrogen is harder to pull off. Okay, the first one's fairly easy. The first one comes off very fast and easy because that's what makes it a strong acid. Because it comes off in a hurry. It comes off very easily. Okay? But to make the second one come off, you've got to have a lot of base in the water. Okay? When you do that, all right, those things join up together and you get water. And now, when we pull that one hydrogen off, we get SO4 and what charge? I've already got a negative. 2 negative. And that's what it is one more negative than we had before. Okay? And then we're still making water. And we still freed up potassium.
What do you mean when you say the number of hydrogens?
When the number of hydrogens that are available to pull off the acid, that's this on this formula right here. When the number of those that are available equal the number of hydroxides in the solution, you reach the equivalence point. This is the second, because now this is the second hydrogen I'm pulling off, this is the second equivalence point on our graph.
So it's just how many hydrogens are pulling off?
Exactly. Yeah, I think that's a pretty good way of saying it. Okay? So this is our second dissociation, which gives us our second equivalence point. All right, is it kind of making sense? Well, this ion here, this polyatomic ion here, was already one negative charge. Okay? If I pull off a positive charged particle here, then I have to make this one more negative. Whatever's left has to be one more negative. Does that make sense? All right. This is the acid because it's giving away a proton to something, right? It's giving it away to the hydroxide, which is part of this, so that's the base. You with me? This is the acid because it's giving away a proton to something else in the Bronsted-Lowry theory. It's giving it away to a hydroxide, and this hydroxide came from this, so while the hydroxide, so is the species it came from, the Bronsted-Lowry base. Okay? So this is our base right here. Then this is our conjugate acid here. Water's an acid here. When you pull the hydrogen off, huh? Spectator. Bench warmer. Got it? Okay. See now, pull the proton off, what remains is the conjugate base, correct? But that conjugate base is also an acid, because here we're pulling off another hydrogen. So it depends on what you're doing with it as to whether you define it as an acid or a base.
So that would be defined as an acid.
Huh?
So you would define the second dissociation is an acid.
Acid. But this is the conjugate base of this acid. This is okay? You with me? Just stick with the definition. It'll get you true. Okay? Base, conjugate acid. Alright? Everybody with me? Water was the base because it accepted the proton. Now water's the base because let's see. Yeah, this OH accepted the proton, and that'd be a conjugate acid. That's an acid, and that's a base. So water can be both, right? This species here, that's because it can be both an acid or a base, depending on what it's doing. You with me? All right. Everybody shake their head and take a deep breath or something, okay? Because we're going to move on. We're going to go deeper here. We're going to drill deeper. Huh? I think we got to. Because you got to know this stuff for the lab on Monday. You don't have to do any of them. Because you can go to jail or you can die. So, anyway. All right. I'll tell you what, let's stop capturing for a moment here.